All right. Well, it is my pleasure to welcome Marc Neveu, who is a research scientist at the University of Maryland, College Park, as well as here at NASA Goddard. And we will be hearing his work on a code to simulate carbon cycling. So, Marc, I will turn it over to you. Thank you so much.
Thank you, Joe. Hi, everyone. Thanks for the chance to speak about this code. I call it ExoCcycleGeo, ExoC for carbon. So it's a code to simulate carbon cycling on planets of variable sizes and compositions. The development of this code stemmed from a project funded by NASA's Exoplanet carbon cycling program to couple geological atmospheric models to simulate carbon cycling on a wide diversity of planets. So you may have heard Sean's presentation on the Atmos code a couple hours ago. Um, we partnered with him and Ryan Felton, who is now at NASA Ames, but was studying with Sean at the time, um, with the capabilities of Atmos to simulate the chemistry and the climate of a planet with various stellar inputs and redox states. And we sought to develop a geologic code that could look at how planet compositions and sizes might affect carbon cycling. So I worked on this with Taylor Bartlow, who was a postdoc student at UMD at the time, and we've been supported by Steve Desch at Arizona State as well. So just a quick recap of the carbon cycle in case you're not familiar. There's atmospheric carbon in Earth's atmosphere that is thought to be replenished by outgassing, as in, for example, volcanism, and regulated by weathering, where rainwater carrying carbon solutes reacts with a rock at the surface. The slight acidity in the rainwater dissolves part of the rock, and the rock cations, as well as the bicarbonate and carbonate, are transported to the ocean, where they can precipitate to form minerals that sink to the bottom of the ocean. Some mineral formation happens also because of seafloor weathering, and then those get subducted eventually and return to the mantle, completing the cycle. The atmosphere itself can affect weathering by the greenhouse effect that can change the surface temperature or the rainfall rate in a negative feedback that has helped regulate the climate of the Earth over geologic timescales. So this is the carbonate silicate cycle without any effect of biology here. And I guess a goal of the project and a goal of the code is to be able to set an abiotic baseline for what the atmospheric composition of a planet might look like without life. So we sought to see how that carbon cycle might change if the stellar UV flux changes with the effects of photochemistry, and then how planet size and composition can affect volcanism and weathering. So the architecture of the model is based on a box model, which is not too unusual for models of carbon cycling. There is a box for the atmosphere plus ocean reservoir, and then we track fluxes between reservoirs. So the atmosphere has CO2, methane, oxygen, water vapor, and then N2, which is at a constant partial pressure. And it's equilibrated with a surface ocean by assumption. And we calculate the detailed equilibrium with the detailed ocean composition using a code called FREAK, which is developed and maintained by the US Geological Survey, widely used in aqueous geochemistry applications. Gases to that reservoir come from the mantle, and the outgassing flux is computed with the help of a geodynamic model. So the terrestrial-sized planet is assumed to form, and it's evolved from formation for billions of years. It's heated by the heat of accretion and the decay of radionuclides, and the heat transport takes place by convection through the mantle and conduction through the lithosphere. The model generates 1D temperature profiles that are then computed with a Celadus curve that depends on the composition of the upper mantle, and that's calculated with a different geochemistry software called MELTS, also widely used. And the comparison generates melt fractions as a function of depth. Those are summed for total melt amounts, and with assumptions on how much melt reaches the surface and how much carbon is in the melt, an outgassing flux is computed. Gases are taken out of the atmosphere through continental weathering. Kinetic reactions are carried out with FRIG, the same software as for the atmosphere-ocean equilibrium, assuming as a model input a crustal composition. The solutes are delivered to the ocean, and then the ocean itself is where equilibration can take place to precipitate minerals, with some subset of the ocean fluids reacting with the crust, depending on the timescale of hydrothermal circulation at the seafloor. The contributions of continental and oceanic weathering are weighed by a factor L, which is kind of the aerial fraction of the planet surface covered by land. And this completes the cycle. So the main takeaways here are that this code is first principles only. So often simulations of carbon cycling start off by taking Earth's present day fluxes from outgassing and from weathering, and then scaling them to, say, the partial pressure of CO2 to some power law or the rainout rate. Whereas here, everything is computed by physical processes and chemical reactions. So it's kind of a departure from an Earth-centric view. And the variety of compositions and of sizes that can be simulated are limited by the applicability of the geodynamics model for size, and then for composition by the range of applicability of the Meltz and Freak models. The code runs forward in time for billions of years after the planet's formation, so the geodynamics are kicked in at formation. The carbon cycling itself is not started until about 0.5 billion years after formation, and this is to ensure that there's a surface ocean that's been in place, that the atmosphere is pretty stable and secondary, and it kind of meshes with Earth's history too. We don't have the magma ocean stage, basically. And finally, the code is written in C language. It needs libraries from Meltz and Freak to run, and all of this is freely available. I'll give you the websites at the end. So here's an example input file. There are different sections. So a grid is set up. A planet's interior is set by specifying a mass, a core mass fraction, planet building materials to get a mass-radius relationship, a radionuclide complement, and then a mass fraction of carbon in the mantle. The surface is initiated with surface ocean mass, an aerial land fraction, initial temperature and pressure, and then the atmosphere is set up with 5 mixing ratios. The composition of the crust for the continents, for oceans, and for the upper mantle is also set up. So I'm just showing snapshots here, but about 50 to 100 minerals can be chosen from, and then the dozen oxides from the upper mantle compositions that are then further speciated into minerals. And so here's an example output. So this is for an Archean Earth planet with a mafic surface and upper mantle, about 1 Earth mass. It takes a few days to get this result on the Mac laptop. So the first plot here shows the evolution of carbon reservoir sizes as a function of time after formation between about 0.6 and 2 billion years. The code also outputs fluxes from outgassing and weathering with a net flux that's usually about 0, so the climate is somewhat balanced. Surface temperature and pressure, atmospheric composition. In this run, there's just a basic greenhouse effect parameterization, so the code can be run standalone without coupling to an atmospheric model. And so there's no photochemistry or anything, there's no methane in this output. The code also outputs pH for ocean water, for rainwater, and then for hydrothermal fluids at the seafloor, and a somewhat detailed ocean composition extract. Just a quick comparison with prior work as a sanity check. So each side of the code has been validated to the Earth. So making sure that the volcanic fluxes computed are similar to what's on Earth today for the same conditions, same surface composition, etc. Same for weathering. But this is a comparison at the full model level. And the background plot is from a review by Dave Catlin and Kevin Zonley in 2020. And then the ExoC output is shown as the inset. The N2 partial pressure is held constant, but the CO2 somewhat meshes with what they had. The gray curve is water vapor, which is not plotted in the background. And then again, the output doesn't have methane because photochemistry is not taken into account. But Ryan is working on some preliminary couplings and finding that the amounts of methane mesh fairly well with what they found. Although there's some tweaks to be done. The temperatures are not quite right, etc., but we're getting there. So just very quickly, I'm not expecting you to see anything on this eye chart other than the column and row headers. So the column headers are the various outputs I just presented, and an example of how outputs can vary for different planet sizes. I didn't mention it, but the code also outputs a few important geodynamic parameters like the mid-mantle temperature, the heat flux at the base of the lithosphere, the convective velocity, the Rayleigh number in the convecting mantle, the thickness of the crust and lithosphere. And here's another set of outputs where here the mass is held constant, but the redox of the planet is changed so to a chondritic upper mantle with more metal, and then forcing the planet to outgas about 50% of methane, and then testing for various haze effects that the high methane to CO2 ratio can generate. So the code is available on GitHub. You see the link here. There is kind of bare bones documentation at the moment, but you're welcome to reach out to me, and I'm happy to help you use it if you'd like. It has some limitations, particularly linked to calling these external codes freak and melts and trying to have them run outside of their range of comfort. So having to run them at each time step sometimes makes it difficult for the code to proceed, but there are ways to restart and to run only portions and then to tweak the composition so it's not too crazy. The links to the main code and the dependencies are shown on the top right. And we have a paper that's going to be submitted at any hour now by all 5 of us, looking at the code developments and then the sensitivities of various parts of the carbon cycle to sizes and compositions. Thanks for listening.
Thank you so much, Mark. That's an awesome talk and really cool tool that you're developing here. Um, if anyone has any questions for Mark, please feel free to raise your hand or post them on the Slack. There was a question in chat that you just answered there, if there's a summary paper, so it sounds like that's in the works and about to come out. I was just wondering if you could kind of just expand upon the limitations right now. You just showed the table of like different planet masses, and obviously this is an exoplanet conference, but does this have applicability to solar system moons and stuff like that? TNOs?
Um, so at the moment, the code is geared toward terrestrial planets. So we've, for example, in the paper that we're about to submit, we looked at the dependency of weathering on planet surface compositions, and we picked surface compositions from various inner solar system bodies, so Venus, Mercury, the Moon, Mars, just to see like if we put an ocean on there and we had the Earth or Archean Earth's atmosphere and it started to rain, how much weathering will we get? At the moment in the code, I mean the weathering, for example, shuts off if the temperature, the surface temperature gets to below freezing, but there is no option to have an icy shell. So it wouldn't work for icy moons or TNOs, etc.